Okay, now power amplifiers. About amplifiers, we have already studied, right? In module 2, we have studied about amplifier circuits, and in module 3, we have also, discussed about multi-stage amplifier circuits. Okay, but so far, whatever amplifiers we have studied, those amplifiers were, belonging to a small signal category. Okay. Now, in module 4, whatever amplifier we are going to study, it is belonging to a large signal category. Okay. Now, what do you mean by large signal and small signal? Okay. So, large signal, okay, and small signal. Okay. Now, large signal and small signal, okay, these two are basically called as the signal levels. Signal levels. Okay, under signal level, you can have a broad classification of two types: large signal and small signal. Now, this large and small signal is basically being derived on the basis of power level. Power level. Okay. Now, what are the constituents of power? The constituents of power are nothing but voltage and current. Okay. So, if your voltage and current signals were to be smaller, obviously your power level going to be smaller. Okay. And whenever we say power, we normally talk about the active power delivered. Okay, which is in the form of I square R or V square by R. All right. So, active power. Now, if E and I were to be small, you can say that it is a small signal amplifier. Okay. On the other hand, if your voltage and current signals were to be large, then you are going to have a large signal. You are going to get a large signal. Okay. Accordingly, your amplifiers are classified into either small signal amplifier or large signal amplifier. Okay. Now this okay, this is small signal amplifier. Okay, I cannot say this is a power amplifier. This is a small signal amplifier. Okay, and a large signal amplifier, which can be called as power amplifier. Okay, so this power term normally associated with large signal amplifier. Okay, now about small signal amplifiers we have already studied in module 2. Okay, now the differences I will list out after some time. Okay, so first let us try to understand why do we need this large signal amplifier or a power amplifier. Okay, so let me consider an example of a loudspeaker. Okay, loudspeaker. Loudspeaker is very commonly used in campaigning purpose, or to that matter, even in case of musical system, what you are going to have is a kind of loudspeaker arrangement. Okay, now if you look at the internal block diagram of loudspeaker system, okay, is basically consisting of several stages. Okay, now to this particular subject, I have considered a public addressing system. Okay, in short, it is called as PAS system. It is something like on one end, the speaker will speak in a microphone, and on the other hand, enlarged signal will come out of the speaker in the form of a sound wave. Okay, so between microphone and between speaker, you will have several substages. Okay, several substages, and those substages are broadly classified into two sections. Okay, voltage amplifier section and a power amplifier section. Okay, so if you look at the block diagram, you would see that a power amplifier occupies in the last stage of a public addressing system. Okay, so this is the position of a power amplifier. So where is it getting occupied? It is getting occupied between voltage amplifier and a loudspeaker. Okay, so this is your source. Okay, and this is your low. All right. Now I'll tell you the significance of each stage. Okay. Now source, okay, is basically a microphone wherein the human is going to utter some voice, right? So basically, this microphone, okay, this microphone will receive, okay, will receive a sound wave. Okay, will receive sound wave as the input, and it gives electrical signal as the output, right? So sound energy is the input, and electric signal going to be the output of a microphone. That's the reason this microphone can also be called as a transducer. Because it converts the energy from sound energy to electrical energy. Okay, now you have to understand one fact is that the order, okay, the order of, or you can say that the signal level of this electrical signal is very, very small. It will be in the order of microvolts. Okay, the typical voltage level of the output of a microphone is in the range of mu V or microvolts. Okay, now if you directly connect this microvolts to this power amplifier, will there be any amplification? There won't be any amplification, okay, due to two reasons. The first reason being low impedance matching. Okay, low impedance matching. That's because your source resistance will be in kilos of ohms, and the input resistance of power amplifier is going to mismatch with the source resistance. Okay, so first is low impedance matching, and the second reason is that your power amplifier, okay, requires an input in the range of, say, a few volts. Are you getting the point? The power amplifier requires the incoming signal, to be there in few volts of level. But what is the voltage level of the output of microphone? It is in microvolts. So, it requires the signal to be there in volts, but you are actually feeding a microvolt signal, right? So there won't be any amplification taking place because your power amplifier will be in inactive state because the signal handling capacity is improper. So that's the reason what you have to do is you have to provide sufficient, intermediate amplification so that the low voltage signal, okay, gets amplified to a reasonable level, and that reasonable signal later on can be given to the input of a power amplifier. So that's the reason you can see a voltage amplifier. So this voltage amplifier is nothing but a multi-stage amplifier. Multi-stage amplifier we have already studied in the previous section, right, in module 2. So this microvolt signal is given to a voltage amplifier, which is a small signal amplifier. Let me write, which is a small signal amplifier. So this multi-stage amplifier basically converts the input signal, which is there in the order of microvolts, to, let's say, to some volts. Okay, so from microvolts to, it converts to voltage in some volts. Okay, now you compare the signal level. Now the output of this multi-stage amplifier is in what level? It is in volts level, right? So this voltage matches with the rating of the power amplifier. Okay, and it also matches with the impedance as well. So you can achieve two things using this multi-stage amplifier. The first thing is impedance matching. Okay, impedance match. And the second thing is voltage level. Okay, voltage level. So two things basically you can fulfill using a multi-stage amplifier. Okay, once you give this amplified signal, okay, once you give this amplified signal, basically this power amplifier, achieves power amplification. Power amplification. Okay, remember one thing, the power amplifier will never amplify the voltage. Okay, the amplification of voltage is done by the multi-stage amplifier. Your power amplifier simply increases the power level of the signal. Okay, so the power level of the signal, normally it will be in few watts. Okay, and that increased power level signal is then given to the loudspeaker, and the loudspeaker will throw the sound waves. Okay, so that's how your public addressing system, or to that matter even any musical system works. Okay, any musical system, if you consider, will have a combination of multi-stage amplifier cascaded to a power amplifier. Okay, and the load is always being the speaker system, and the source normally it can be a microphone in case of public addressing system, or in case of musical system it can be the track, mp3 track, or the any other audio signal that you are going to play. Okay, so this is the broad understanding of the role of a power amplifier in communication system. Okay, is this understood?
Yes, sir.
Okay, so once you understand this, you can quickly take up the next topic, which is the difference between large and small signal amplifier. Okay, all right, so couple of differences I have already listed out, okay, pointed out while explaining the public addressing system. Okay, the first difference, okay, going to be in case of small signal amplifier, voltage is amplified. Voltage is amplified. Okay, what I will do, better I type it. Okay. Okay. On the other hand, in case of large signal power amplifier, okay, what is getting amplified? Power. Okay, power is amplified. That's the first difference. Okay. The second difference is about the model which you are going to use. Okay, in case of small signal amplifier, you will use H model or RE model for analysis. Okay. We use H model or RE model for analysis. Okay. On the other hand, for a large signal power amplifier, okay, since you're not going to amplify the voltage level, so you cannot use H model or RE model. So instead, okay, so instead we go for graphical type of analysis. So instead of H and RE model, okay, graphical analysis is carried out basically. Graphical analysis is carried. Okay, so that's the second difference. Okay. The third difference is something to do with the distortions. Okay, distortions. Your small signal amplifier is free from harmonics. Have you come across the term called harmonics? On the other hand, in the large signal power amplifier, harmonics are present. Okay. The harmonics are basically the disturbances present in the output in simple terms. Okay. For example, if you give an input voltage having 50 hertz frequency, okay, and if your output signal is consisting of only a 50 hertz, signal, then you can say that the process is free from harmonics. Okay, so if your fundamental frequency, which is of 50 hertz, is present in the output, okay, and your output is not consisting of any other signals, okay, only it is consisting of a signal which is having fundamental frequency, then you can say that that particular wave is free from harmonics. Okay. On the other hand, if you feed 50 hertz signal to a particular system and your output is consisting of the 50 hertz signal as well as non 50 hertz signals, okay, it could be 100 hertz or 200 hertz or 300 hertz, then you can say that your output is suffering from harmonics. Okay, so your small signal amplifier is free from harmonics. Okay, that means to say your output is consisting of only fundamental component, but your large signal power amplifier will have fundamental component along with even and odd multiples of fundamental component, which we will be discussing it in the future classes. Okay. Next, for small signal amplifier, okay, for small signal amplifier, normal transistor is sufficient. Normal transistor is used. Okay. On the other hand, for a power amplifier, you cannot use a normal transistor because the power rating will be, higher than the small signal amplifier. That's the reason you have to use power transistor. Power transistor. Okay, and the next difference could be in terms of power rating. Okay, power rating. Power rating. So power rating of small signal amplifier, normally it is in the range of few milliwatts. Okay, let me write in bracket milliwatts. Okay, it is double L, right? Yeah. On the other hand, in case of large signal power amplifier, power rating will be in few watts. Few watts. Okay, few watts. Since power rating is very low in case of small signal amplifier, it doesn't require heat sinks. Heat sinks are not used. Okay, I think I have told you in the introduction class of laboratory, the heat sinks. Whenever heat sinks are cooling mechanism, because when your device gets heated, okay, what happens is that the semiconductor device can undergo thermal breakdown. Okay, thermal breakdown is nothing but with the increasing temperature, what will happen? The electron and hole pair inside the device starts increasing. So due to which, what happens is that there can be an avalanche effect that can eventually, destroy your device due to thermal phenomenon. That's the reason it is called as thermal runaway. Okay, so heat sinks are not required for small signal amplifier because power rating is very, very small. On the other hand, your large signal power amplifier requires heat sink. Heat sink. Okay, the next difference could be on the basis of size. Okay, since there are no heat sinks, since you are using a smaller transistor, so smaller size. Okay. On the other hand, since it is having heat sinks and then it is also using a bigger transistor in order to cope up with higher power levels, and also it will have some transformers for impedance matching purpose, etc., etc. So all these factors will add up while deciding the size of the device. So basically, size is bigger. Size is bigger. Okay. And yeah, distortion. So distortion is less. Okay. Okay, and here you can say that distortion is more. The distortion is more. And few more differences could be, okay, power handling capacity I have already discussed. Here, output current and voltage swings are small. You can say that output current and voltage swings are small. On the other hand, voltage and current swings are all large. Okay, the vice versa case you are correct. Voltage and current swings are large. Okay, and you can say that it is primarily used as voltage amplifier. Voltage amplifier. That is, the objective is to increase the voltage level. On the other hand, the large signal amplifier is meant for amplification of power. Okay, so used in amplification of power. Okay, so these are the main differences. Oh yeah, of course, there's one more major difference is that the operating point or Q point. So in case of small signal amplifier, Q point is always set at the center of the load line, right? On the other hand, in case of power amplifier, Q point location varies from amplifier to amplifier. Okay, from amplifier to amplifier. So I'll highlight this particular point. This particular point, because our next discussion is based on the last point. Okay, all right. So this is about the differences between small signal and large signal power amplifier. Okay, any doubts in this? If you haven't understood, any of the difference, you can let me know. I'll try to explain once again. All good? Can I go ahead?
Yes, sir.
Okay, fine. So classification of power amplifier, okay, which is very, very important. The difference they may ask or they may not ask, but classification of power amplifier, normally they will ask for 6 to 8 marks. Okay, all right. Now, in a previous discussion, I had pointed about the Q point operation, right? So I had mentioned that in case of small signal amplifier, okay, you are going to fix your Q point always at the center of the load line. Okay. On the other hand, in case of power amplifier, I had mentioned that Q point location varies from amplifier to amplifier. That means to say, you will not have a one fixed set of amplifier. Instead, you may have different types of power amplifiers. Okay, so based on the location of Q point, okay, based on the location of Q point, the power amplifiers are majorly classified into 5 types. Okay, Class A power amplifier, Class B power amplifier, Class C power amplifier, Class AB power amplifier, and the final class is Class D power amplifiers. Okay, 5 types. Okay, But in our syllabus, we are going to talk about class A power amplifier and class B power amplifier. Okay. Class C, we are not going to discuss in detail, and class AB as well as class D, we are not going to discuss in detail. Okay. I'll explain one after the other. Okay. Now, the next explanation is solely based on the graphs. Okay, I'm not going to do any quantitative assessment in the next explanation. Okay, so what I will do, I will increase the picture size so that you'll be able to see clearly. Okay, all right. So the very first amplifier that we are going to discuss now is a class A power amplifier. Okay, now in case of class A power amplifier, okay, the major features, okay, of class A power amplifier is about the location of Q point. Is about the location of Q point. So if you see the transistor output characteristics, okay, once again, this graph is being drawn on the basis of common emitter amplifier. Okay, common emitter amplifier is considered. That's the reason you can see that output current is taken as IC, which is projected along y-axis, and output voltage is considered as VCE, which is projected along VCE. Basically, it gives VI characteristics. So this is V naught is equal to VCE. Okay, of course, the RMS value of AC signal we are going to consider. Okay, fine. So that is the one thing. So throughout our discussion, we are going to consider a common emitter configuration based amplifier circuit. All right. Now, that is one thing. The second important observation is that you look at the position of Q point. Let me highlight with a blue color. The Q point is placed right at the center of the load line. Okay, so this is the load line. Okay, I will not explain how exactly you construct the load line because we have already constructed the load line in module 2. So Q point is found at the center of the load line, due to which what happens is that if you look at the base current signal, you will get a symmetrical base current signal. Okay, what do you mean by symmetry? The positive half cycle, okay, if it is matching with the negative half cycle, you would say the signal is symmetrical in shape. Okay, so by placing the Q point at the center of the load line, what you get is a complete 360-degree swing of the input signal. Okay, so transistor is a current control device. That's the reason the input signal is considered as the current signal, which is nothing but the base signal. Okay, so base signal exists for complete 360-degree duration. Okay, so this is called as complete swing. Okay, this is called as complete swing. Since base signal exists for complete 360-degree duration, or rather I can also say that when there is a one full cycle of base signal, you will have a one full cycle of output current, that is the collector current, and one full cycle of output voltage, which is VCE. Okay, now let us look at the waveforms. So this is your base signal, which exists for one complete cycle, that is 360-degree, because one cycle is equal to 360-degree. Okay, so due to which there will be a complete flow of collector current, and also you will have a complete collector to emitter voltage signal. Okay, now if you observe your output voltage, that your output voltage is starting from negative cycle. Okay, may I know the reason? We have already discussed in module 2 why we have shown the output voltage in the negative cycle. Can anyone tell me quickly? No worries, if you don't tell, I will only tell. Fine. So that's because common emitter configuration gives 180-degree phase shift. 180-degree phase shift between Vi and V0. Okay, Vi and V0. Okay, that's the reason normally, while sketching the waveform, voltage signal is drawn from negative half cycle. So first half cycle going to be negative half cycle, followed by a positive half cycle. Okay, so this is about the physical, difference of class A power amplifier. Okay, so what you have to do is you have to draw this output characteristics, and you have to draw the waveform, and then you have to claim that there is a complete flow of current at the base terminal, collector terminal, and collector to emitter voltage. Okay, now by fixing the Q point at the center of the load line, you will get a complete 360-degree waveform. At what cost? At efficiency, at a reduced efficiency. So though you are fixing the Q point at the center of the load line, in case of power amplifier, what happens is that conversion efficiency becomes very, very small. Is very low. Okay, it is as low as about 25%. Okay, the conversion efficiency is about 25%. Okay, and with a transformer, you can increase it to 50%. Okay, or up to 50%. That's the maximum conversion efficiency you can expect from a class A power amplifier. Okay, I'll tell you why exactly you get lower efficiency in spite of getting a symmetrical output waveform. Okay, we'll discuss in detail when we take up class A power amplifier topic. All right, fine. So that's about the class A power amplifier. Okay, now let us look at class B power amplifier. Okay, class B power amplifier. Okay. Now, in case of class B power amplifier, remember in class A power amplifier, the Q point was at the center of the load line. Okay, so here I'll write, since there is no space, Q point is in active region. Okay, Q point is in active region. The center region is active region. Okay. On the other hand, in case of class B power amplifier, okay, in case of class B power amplifier, you will see that the Q point is placed. Okay, Q point is placed in the cutoff region. So let me write here. Q point is placed in cutoff region. Okay, so by placing the Q point in cutoff region, what happens to the waveform? Okay, so the transistor, will be alive only for one half cycle. So for one half cycle, you will have the positive pulse of the base signal. Okay, in the another half cycle, what happens is that the transistor gets into cutoff region. So this is your cutoff region. Cutoff. Okay, and if you consider NPN transistor works only for positive voltage level, right? So the transistor will be conducting only for one half cycle. That means to say the conduction angle or conduction period. So conduction angle is 180 degree because it works only for, let's say this is your base signal. Let me extrapolate. Okay, base signal. You will have only one half of the base signal. So this is your IB. Okay, only 180-degree duration base signal is present. On the other hand, for the negative half cycle, the transistor will not conduct simply because it cannot work for a voltage which is less than 0. Okay, so due to the 180-degree flow of base current, you will have a collector current which is lasting for only 180-degree duration. And similarly, your output voltage will also be lasting for only 180-degree duration. So the conduction angle is 180-degree for a class B power amplifier, and the location of Q point is at the cutoff region. Okay. Okay, due to which what happens, basically your waveform will have, sorry, I will not write it here. Okay, due to which your waveform will have distortion. So will have distortion in the output. Okay, you can see, right, output. Your input may be a complete 360-degree cycle wave, but your output will be of a wave which is having only 180-degree duration. Okay, so if you see properly, your output is consisting of only the negative half cycle. The positive half cycle is clipped. Positive half cycle is clipped. That's the reason we are saying that output will have distortion. Okay, output will have distortion. But due to the reduced current flow, because now the current is flowing only for 180-degree duration. So due to the reduced current flow, conversion efficiency will increase. Okay, conversion efficiency is up to 78.5% in case of class B power amplifier. So that's the difference. Okay, so next we have class C power amplifier. So in case of class C power amplifier, what we do is we push the Q point deep into the cutoff region. Okay, so here is your Q point now. See, so x-axis is your cutoff region. Okay, and you are trying to push the Q point deep into the cutoff region. Now, by doing so, what happens is that, okay, let me draw the base current signal here itself. Okay, so Q point is the reference point for the wave to start with, right? So this is your base signal. Okay, this is IB. Now, the signal is present only if, the signal is found above the x-axis, because only above the x-axis the voltage level is positive, and when the voltage level is positive, then only the transistor gets into conduction. So only this thick part of the wave is present in reality. Okay, now what is the duration of its presence, which is less than 180-degree? Because to have 180-degree, you should have the case of class B power amplifier, but here you're pushing the Q point below the cutoff region. That's the reason the signal flows for less than 180-degree. Okay, so this is the observation. Conduction angle is less than 180-degree, and Q point is found below the cutoff region. So due to which what happens, your collector current exists only for a smaller duration of time, and the duration is less than 180-degree, and similarly your output voltage exists for a smaller duration of time. Okay, since the current flow duration is very, very small, okay, you can expect that the conversion efficiency is a lot larger. Okay, so conversion efficiency is large. Okay, large. Okay, so it can be as high as up to 90%. Okay, because conversion efficiency directly proportional to the current flow. Okay, the duration for which the current flows through the load, because efficiency is normally found by finding out the output power delivery to the input power, right? So power delivery is basically I square into R. So if current is bigger, the power delivery will be bigger, and there can be more losses also. Okay, fine. So that's the conversion efficiency. What about distortion? The distortion is very high. Okay, because though your input is a complete 360-degree uh, voltage, your output voltage will have a signal, okay, which is existing only for less than 180-degree duration. So input may be a perfect sinusoidal signal, but your output not going to be a sinusoidal signal. Instead, the output going to be a pulsed output. Okay, so you are going to get pulsed output. Okay, and therefore distortion therefore distortion is very high. Okay, distortion is very high. All right, so that's the difference of, I mean, the important features of class C power amplifier. Okay, now let us look at the last type, which is called as class AB power amplifier. Okay, now this class AB power amplifier is kind of an hybrid, okay, amplifier. Okay, so it is falling in between class A and class B, in the sense the conduction angle, okay, conduction angle is greater than 180-degree but less than 360-degree. Okay, you had seen that the conduction angle of 360-degree you will get it for class A power amplifier. On the other hand, for a class B power amplifier, the conduction angle is 180-degree, right? This is for class B. So in case of class AB, the conduction angle is greater than 180-degree and smaller than 360-degree. Okay, so that's the reason this Q point. Okay, Q point is not found on the x-axis. Instead, the Q point is found slightly above the x-axis. Okay, due to which what happens to base current. Okay, so this is the Q point. Okay, and let me take yeah, this as the reference line for the upper limit. So this is how the base current signal going to look like. You have complete 360-degree, I mean 180-degree positive half cycle, but in a negative half cycle, you will have only this portion and rest all is like clipped. And again, the negative half cycle comes into picture. So you can clearly observe that wave exists for more than 180-degree, but less than 360-degree. Okay, so that's the reason you see your collector waveform. Same thing, you'll get a complete positive half cycle and a fraction of negative half cycle. That's the reason the collector current flow is greater than 180-degree but less than 360-degree. Similarly, you will get your output. You will get a complete negative half cycle but a clipped positive half cycle. Okay, so that's the reason your conversion efficiency going to be greater than class A. Okay, sorry, let me write it in this way. Conversion efficiency is greater than class A but less than class B. All right, conversion efficiency is greater than class A but less than class B. Okay, and the Q point location also, right? I can write Q point is located slightly above the cutoff region. Cutoff region. Okay. And distortion is less compared to class B, because class B amplifier gives an output which is lasting long for only 180-degree duration. On the other hand, class AB gives an output which is lasting long for more than 180-degree but less than 360 degrees. So distortion is less compared to class B but more compared to class A. Okay, so this is about the different types of power amplifier circuits. Okay, power amplifier circuit. All right. So, any doubts in this? Any doubts in this?
No, sir.
No, clear, right? So, you know, this normally they will ask. Okay, fine. So, in the next class, what we can do is we can start with the analysis. Okay, first let me write down the syllabus. Analysis. Now, in the analysis, only two power amplifier circuits are considered. Okay, class A power amplifier. Okay, in class A, we have two types: transformer-less, which is also called as series fed class A power amplifier. Okay, this is the first type, and the second type is transformer coupled. Transformer coupled class A power amplifier. Okay, so in the analysis, our main objective is to find an expression for conversion efficiency. Okay, that is eta conversion. Okay, conversion efficiency, and also expression for maximum efficiency. What could be the maximum conversion efficiency under ideal conditions? Okay, so that's about your class A power amplifier. Okay, and the second type what we are going to study is class B power amplifier. Okay, power amplifier. In class B power amplifier, again we will have two types. Okay, the first type is transformer coupled. Class B, and the second type going to be complementary symmetry. Okay, which is transformer less class B power amplifier. Complementary symmetry class B. Okay, once again we will be talking about the conversion efficiency and the possible conversion efficiency, the possible maximum conversion efficiency which you can get it from a class B power amplifier. Okay,